Howdy! Chapter 1, Coulomb's Law. In the study of mechanics, we learned about many forces, such as that exerted by a spring or the push exerted by some person. Always there was an agent exerting the force, except for one force. The mysterious force of gravity that acts on an object, seemingly with no agent coming in contact with the body. In high school, we hid our ignorance by giving this kind of force the name action at a distance. Just giving it a name does not mean we understand it. In fact, we really don't believe there is such a thing as action at a distance, but rather attribute such a force to the exchange of particles. Suppose there were two boys on skateboards and they wanted to repel each other. How could they do it without touching each other? They could have a number of objects such as bricks that they threw at each other. The thrower would recoil after each throw, and the catcher would recoil after each catch, according to the law of conservation of momentum. This repulsion does not seem at all mysterious. If the bricks were transparent, we might think of this repulsion as magic and maybe give it the name action at a distance. If the boys were throwing invisible frisbees instead of bricks, we could construct an attractive force by a similar exchange. This model at least gives us an idea about the force of gravity. We are all hopefully experts in looking at a system, drawing the famous free body diagram, and applying the laws of mechanics to predict motion. We can do some experiments that show there must be additional mysterious forces acting on some objects that do not have an apparent agent similar to the force of gravity. Just like to show you that there are things that we would not understand if we did not know about electrical and magnetic forces. For example, from Physics 218, if we were to isolate this balloon and ask what happens if I put it against the wall, we would all agree that it just falls down. Will it act any differently if I rub it first on my shirt? Should make no difference whatsoever. Definitely a mystery until we understand about charged particles and the interaction between charged particles. So there is another force besides gravity, springs, people pushing, and this entire course will be studying such forces. There's another force which has nothing directly to do with electrical forces. Here we have a piece of material. I'm not sure if you can see this. And without touching it, I can make that arrow spin around. I can make it go in that direction, away from my hand, or I can make it follow my hand around. This is a magnetic force, and we'll have to study the basics of magnetic forces. And one might ask, why would an engineer care about static electricity, any kind of electricity, magnetic forces? And the answer is, essentially the only way to generate electricity is to have a source of a magnetic field, move a loop through a magnetic field that will generate an electrical current. And essentially all generators work this way. Either you use nuclear power, coal, natural gas to boil water, to make steam, to turn a turbine, replacing my hand. Another demonstration of the connection between magnetic forces and electrical forces. We have an electrical force pushing charges through this filament in an ordinary light bulb. That's why the light bulb is on. If I bring a strong magnetic field close to the filament, strange things happen. Also something we will understand when we are finished with Physics 208. Just as Newton postulated a law which was to describe the gravitational force between two massive objects, Coulomb postulated a law which describes the electrical force between two charged objects. It is a vector law very similar to the law of gravity, and most of what we will learn about electricity in this course follows from Coulomb's law. According to Coulomb, if there are two small particles with charges q1 and q2 separated by the distance r, there will be a force they exert on each other with magnitude given by F equals a constant q1 q2 over r squared. And the direction will be along the line connecting the particles. It will be repulsive if the charges have the same sign and attractive if they have different signs. The force on the compass needle in the video is a magnetic force which we will only study in Chapter 9. We will see that there is an unexpected connection between the magnetic and electric force, which was discovered by Faraday, and this led Maxwell to discover the electromagnetic nature of light. This, as well as an understanding of all electrical circuits, is the goal of this course. One surprising experimental result is called superposition. Based on our picture of forces resulting from the exchange of particles, it would be natural to assume that having three boys throwing bricks at each other would mess up the law describing the force between two boys. After all, sometimes the brick thrown by one boy will interfere with the brick thrown by another. In fact, experiment shows that this is not the case. When three objects are present, the force exerted on each one is just the vector sum of the two individual forces, at least in the simple cases we will initially study. Summary. You will need to understand Coulomb's law so that you are able to calculate the force that one charged particle exerts on another. You must know how to add the forces exerted by a number, whether infinite or finite, of charged objects on another charged object using Coulomb's law and superposition. Gig 'em!